Satya Majumdar, and unless you've changed the title, a sluggish random walk with subdiffusive spread. Okay.
Okay, so good morning, everybody, and so let me first start by thanking the organizers, Luca and Anastasia, for the kind invitation, and it's always a pleasure to come back to Newton Institute. It's really a great place. So today I'm going to talk about, since this is a conference or workshop on anomalous diffusion, I'll talk about a very simple random walk model in inhomogeneous environment, which exhibits a subdiffusive growth, and I'll discuss the mechanism of that, how that comes about. And this is a sort of recent work which was done in collaboration with Rosalind Allen, who was in Edinburgh University till last year and then moved to Germany, and Martin Evans, who is my long-time colleague from University of Edinburgh, and Aniket Jodaj, who was a master student of Rosalind last year in Edinburgh, and now he is doing his PhD in California, San Diego. And also then I'll talk about a little bit of more recent extension of this work, which was done in collaboration with Giuseppe Del Vecchio, who has just started his postdoc in our group at Orsay. And for some reason, he writes his surname as Del Vecchio squared. Okay, why not? So anyway, so this is the sort of program. And so here's the outline of my talk. So I'll start by talking about the mechanism of slow dynamics in a very simple setting, namely just a single particle moving in a random rugged landscape, random or inhomogeneous rugged landscape, and then I'll introduce this particular model that I'm going to focus on, which we call the sluggish random walk model, and I'll explain the meaning of the word sluggish. And it turns out that for this model, you can actually find the exact solution for three main observables, namely the position distribution of the random walker at time t, then survival of the first passage probability, and also the distribution of maximal displacement, that is the extreme value statistics up to some time t. Then I'll talk about the generalization to other solvable models, and then finally I'll conclude with a summary and some outlook. Now, at the outset, I should say that I'm a physicist, and I know this is a mixed crowd. I mean, some of you are mathematicians. So this talk is prepared in the style of a physicist, which means that I won't state my results in the form of theorems, but at least the results will be explicit, and hopefully the main ideas will be clear. Okay, so let's start. So the basic setting is very simple. So you have just a random potential landscape in one dimension, and you have a particle moving in this random landscape. Okay, and so what happens is that as time goes, the particle gets increasingly trapped in deeper and deeper wells. So this is a rugged landscape in the sense that there are the typical realization of the landscape has many local minimum and local maximum, and as time goes, the particle sort of gets trapped into a local minimum like this, and it takes a long time to go over the barrier and to move forward. And this is the mechanism for the slow dynamics, because it sort of spends a long time in local minimum before it can get out and cross the barrier and go move to some other points here. And in fact, the typical time scale for to hop over a barrier is what is in physics is well known, is called the Arrhenius law, which says that the typical time takes is exponential beta Lk, where beta is the inverse temperature and Lk is the height of this barrier, the potential difference between these two sides. I mean, I understand that some of you probably are not familiar with this Arrhenius law, so let me just spend a few minutes to explain to you a little bit where it comes from. So it's best explained in terms of a lattice model. So imagine that you have a one dimension, you have a lattice, infinite lattice. These are the lattice points. And the sides are labeled by, let's say, k. This is k plus 1, etc. And at each side of the lattice, you have a scalar variable, which is like the potential. So this is Vk plus 1, etc. Okay. So So once you give me this set of vk's, so they define my landscape. This is the landscape, if you like. Now this could be random variables, or it could be just some deterministic function, but it's inhomogeneous, it depends on k. Okay, so given this background landscape, and now imagine that a particle is hopping on this landscape. So it's doing random walk on this landscape, and so this is a Markov chain, and with the transition probability, so imagine that the dynamics is taking place in discrete time. Probability from site k to k plus 1, I'll denote it by this transition probability wk to k plus 1. And this is sort of taken to be some constant times exponential minus beta into this potential vk. Okay. So for the moment, this beta is just a constant again. Okay. So this is the transition probability. And so this transition probability, then the position distribution P of kt, probability that the particle is at site k at time t plus 1, it evolves by the master equation, which is okay. So this is just as that if it is a site at time t plus 1, if it was at site k, it stays there with this probability. This is the going away probability. 1 minus that is the staying probability. And if it was at some other site k prime, then with this transition probability, it comes to site k, and therefore okay, so that's the sort of evolution equation over the position distribution, master equation. And now with this particular choice of this transition probability, so suppose that I now define a measure which is called the Gibbs measure, and this is just some proportionality constant normalized, and is supposed to be normalized. So this is the Gibbs measure, and what you can check, given this transition probability, that it's very easy to check that holds for all k, and you just plug it in, and you can check this. And this is what is called the detail balance condition. And once you have this detail balance condition, then you see from this master equation that each of the terms inside the summation, so if you put this pkt in the long term limit to be the p Gibbs k, each of the term vanishes separately for each term. And therefore, what it says is this detail balance condition guarantees that this pkt in the long time limit, it approaches to a stationary distribution, which is just this Gibbs state basically. All right, so this is the sort of very basic things. And then you can ask, okay, how long does it take to hop from site K to K plus 1? So what's the typical time it takes to hop? Because in discrete time, it tries many attempts, and some of them are successful and some of them are not. So, so essentially this W, K to K plus 1, and suppose that the typical number of steps is tau typical, okay? And you set to be 1, because this is the total number of attempts, and so the expected number, this is the probability to actually move there. So this is the expected number of hops to the successful hop to the right. And so if I make one hopping from site K to K plus 1, then the typical time scale is just given by this, just an estimate essentially. So let me put it order 1. So this means that tau typical is actually 1 over the transition probability. And since the transition probability is e to the power minus beta Vk, so therefore this goes like exponential beta into, oh sorry, I made a mistake here. I should say this is Vk plus 1 divided by minus beta Vk. And I'll call this as Lk, the height difference between the two sides. And therefore, you know, so what you find is that this goes like e to the power beta Lk. And this is what is called the Arrhenius law. And this is the sort of, you know, the crucial thing, that the typical time it takes to move one step, one hop, is inversely proportional to the transition probability. And that transition probability for this particular choice, it goes like e to the power beta into the barrier height difference, Lk. And that's the sort of Arrhenius law. Okay. So for instance, I mean, one very classic, well-studied problem is the so-called the Sinai model. So in the Sinai model, so you assume that the landscape here is just a Brownian motion in space, the trajectory of a Brownian motion in space. And so that's your landscape. And so in that case, you know that the Lk, the typical height of this landscape, because it's a Brownian motion in space, so it goes like square root of k. This is just a heuristic scaling argument, but it gives you the time scale correctly. So Lk goes like square root of k, therefore tau, time required to go over the barrier, is e to the power beta square root of k, and consequently the k, the distance, scales like log square of tau, which is very, very slow dynamics at long times. So these kind of, typical scaling arguments, these are very powerful tools for physicists. I mean, they are heuristic, they are not rigorous, but often they give correct answers, and they are very useful to guess the final asymptotic laws for the growth. All right, so this is the simplest model that people that shows the subdiffusive growth. Now, another class of models, which are lattice models, and these are called trap models. And this is basically exactly similar as the model I discussed here, except that instead of defining the potential at each side, you just define in terms of this potential difference, Lk, and you say that, okay, at each site, so you have a trap, which is of depth Lk, and if the Vk's are non-decreasing function, these Lk's are all positive. So it's like each particle comes to a particular site, and there's a trap there, and it gets trapped for a very long time till it sort of goes over this barrier and moves to the next site. And so if Pk is the transition probability, this Pk is exactly Wk, k plus 1. So Pk is the transition probability, let's say, to the right, and Pk to the left, and 1 minus 2 Pk is the probability that it stays at that site in one step. And so in typical trap model, these models are used very much, quite extensively to study, for example, the slow dynamics in glasses, granular materials, and many, many other systems. So yeah, as I said, Pk, little pk, I'll use the notation little pk, which is just exactly this transition probability Wk, k to k plus 1, the hopping probability from site K either to the left or to the right. Here I'm just assuming symmetric. And okay, so in the trap models, typically these are LKs are quenched random variables. The trap depths essentially are quenched random variables. And again, the Arrhenius law holds, which means that the transition probability is inversely proportional to the time to hop, time required to hop, and therefore this goes like e to the power minus beta LK. Consequently, these PKs are also quenched random variables. And then you can study various other properties, and this sort of leads to many interesting properties. So for example, the weakly broken ergodicity. So ergodicity is never broken here really, because eventually the system does reach the Gibbs state, but it does so extremely very slowly, as you saw from the Sinai model. And this kind of slow dynamics also leads to other interesting properties that people observe in experiments in glasses, like edging properties. That means if you look at the 2-point correlation function of the position, then it depends on both coordinates t and t prime, and not on this difference between them. So this is called the edging behavior. And there are many people who have studied these problems. This trap model this version was introduced by Jean-Philippe Bouchot in 1992, and followed by many people studied, including people in the audience here. All right, so this is the sort of disordered systems where these are quenched random variables. But you can also study this problem even when these LKs or PKs, if you like, the transition probability or the depth, they are equivalent. So they are non-random variables, but they are some deterministic function of K. Okay? For example, it could be that the LK is increasing in some fashion here, and then as it goes and goes, it spends longer and longer time in deeper and deeper wells, and which slows down the dynamics considerably. And so for this model, this inhomogeneous random walking inhomogeneous system with these PKs defined as the hopping probability from site K to K plus 1, the position distribution P of KT, it sort of evolves by this Markov chain rule. So the probability that site, it's at time T plus 1, it's at site K. That means at time T, it was at K minus 1, and it made a hopping from K minus 1 with this rate, with this probability P K minus 1. If it was at K plus 1, it made a hopping from K plus 1 to K with this probability P K plus 1, and with this probability it stays at the site K. So this is the basic Markov evolution rule, and in fact, these kind of equations appear in many different problems in evolutionary biology in particular, where for example, this could be the population size of a particular allele or cell, and how it evolves with time and so on. And but in general, these equations are very hard to solve for arbitrary, P of K. Even though this is sort of linear equation, but they are not so easy to solve for general P of K. Okay? And in particular, this is just the probability distribution of the position, but there are other observables. For example, you can ask the survival probability. That means, suppose that it starts at some point, what is the probability that it does not cross the origin up to time T? Okay? So this is the derivative of the survival probability is just the first passage probability, first time it comes back to the origin. Or for example, you can ask how far it got displaced up to time T. That is, what's the maximal displacement? This is extreme value statistics. And these observables are even harder to compute in general for an arbitrary P of K. So there is one model for which all these observables can be computed. It was studied in the mathematics literature for a very long time, and this is called the Gillis model. So this Gillis model was introduced in 1956, and here the hopping rules are the following. So essentially, you have again a one-dimensional lattice, and from site K there's a parameter epsilon. So it moves to the left. So there's a bias. It moves to the left as 1 plus epsilon over mod K times half, and it moves to the right with probability 1 minus epsilon by mod K to the power half. And if it is exactly at origin, it goes equally probability half. Okay? And so this parameter epsilon is like a bias. So if epsilon is positive, that means there's a bias towards the central bias, and it's symmetric around K basically, both sides. So there's a central bias towards the origin. If epsilon is positive, there's a more probability to move to the left than to the right. And if epsilon is negative, that means there's a bias away from the origin. So this model has been well studied by various people, And again, the Markov evolution rule for the position distribution is just simply very simple rules. But it has a very interesting behavior. So what happens is that what you can show is that, what people have shown, that in the long time limit, this P of kt actually has a stationary distribution only if this parameter epsilon lies between half and 1. So its range is between -1 to +1. If it is between half and 1, that means there is a bias towards the center, okay, from both sides, bias towards the center. And so there is a diffusion and there is a bias towards the center. They compete with each other and it reaches a stationary state. But it happens only when this parameter half epsilon is between half and 1. But if epsilon is less than half, then there is no stationary state. But in both cases, in all the cases, for any epsilon, the x squared t, mean square displacement, actually depends on time. In fact, if epsilon is between -1 and half, when there is no stationary state, it's always diffusive, t. But when there is a stationary state, so stationary distribution exists, but it has a power law tail. That means, the second moment is divergent to the limit, long time limit, t goes to infinity. And for finite t, finite but large t, it grows subdiffusively as t to the power 3/2 minus epsilon, where epsilon is this parameter here. So exactly at epsilon equal to half, it becomes diffusive, but otherwise it's subdiffusive. And so this is quite interesting. And in fact, this model has been very well studied in the physics literature also, because if you look at the continuum limit, that means when k is very large and time is very large, you can just do a Taylor expansion of this. You just do a Taylor expansion for large k and just write the continuum equation for P of kt. And the continuum equation is just a Fokker-Planck equation which has this form. So there's a diffusion term and then there's a drift term.
Oh, so, there is a question.
Yeah, sure.
Sorry, can you go back to your previous slide?
Yeah.
What do you mean by mean square distribution? You mean a variance?
No, mean square displacement, just the variance of the position, k squared t basically, if you like. And all right, so in the continuum limit, it's very easy to understand because what happens is that this is just a Fokker-Planck equation. There's a diffusion term, okay, this is just a diffusion term, and then there's a drift term. So as if there's an external potential, and this potential for if you just work it out, the continuum limit, it turns out to be just this 2 epsilon log of mod k, where epsilon is the parameter, central bias parameter. So for epsilon positive, so you have for epsilon positive, you have a potential which is positive, which means that it's repulsive away from the origin, whereas epsilon negative means that, epsilon positive means that the potential is attractive towards the origin, and epsilon negative means it's opposite. And so you can understand why it goes to a stationary state for a certain range of epsilon, because then it goes to a Gibbs state, and which is normalizable for that range of epsilon. And this particular model of particle moving in a logarithmic potential, it appears in many different physical examples. For example, the vortex dynamics, or the tracer particles in a driven fluid, cold atoms in optical lattices, and then system with long range interactions and so on. And several people have studied in detail this continuum version of the Gillies model, if you like. Okay. And it's quite recent works. All right, so this is the sort of background. So now let me come to the main model that I want to talk about today, which is the sluggish random walk model. And as I said, in general, very difficult to solve this kind of inhomogeneous random walk problem for arbitrary P of k, transition probability. The Gillies model is just one exception. And here I want to show you that there is another model which I'll discuss now, where again you can solve for all the observables exactly. Okay. So what is this model? So this model is very simple. And the observables that I'll study are these 3 observables: the position distribution that I mentioned. I'll talk about the survival of the first passage probability, and I'll talk about the distribution of the maximal displacement. That means maximum displacement up to certain fixed time t to one side. Okay. So what is this model? So the model is again exactly same thing. So you have a lattice, and it's like a trap model. So you have a trap, but these traps are non-random variables, but they are deterministic, and they grow like this is the LK, and in the hopping probability pk from side k to k plus 1, is just 1 over mod k plus 2. This 2 is not very important. It's done such that for k equal to 0, you have probability half to the right, half to the left. Okay, so it's just a cutoff essentially. So basically, it goes like 1 over mod k for large k. Okay, and so this means since pk by Arrhenius law is just e to the power minus beta lk, so this means that the trap length, if you like, lk, it grows logarithmically for large mod k, and with this parameter 1 over beta. Okay. So this why we study this particular choice of pk. What's the motivation for it? So this motivation is a little bit convoluted and tortuous. I mean, our original motivation actually came from a biological problem where, when you have drug-resistant bacteria, what happens is that you have microbial, population of bacteria growing, and when you put antibiotics, some of them actually undergo some mutation and become drug-resistant. And it's very important to study, how these drug-resistant bacteria grow. So how does the population of this mutant population, drug-resistant bacteria, grow with time? So there have been experiments and people have been studying this. And a simplified version of that model where this, pk of t is the population distribution of the mutant population in a certain what is called the active layer. But okay, but this connection is a bit too long and tortuous, so I don't want to get into the discussion right now. But you can just think of this as a very simple random walk, inhomogeneous system model with this rate. And we'll see that with this particular choice of the rates, we can actually solve many things exactly. Okay. So, all right. So first, let's again use a heuristic scaling argument to see what would be the growth law. How does the distance scale with time at large times, basically? Okay. So for this, again, I'll use the exactly similar Arrhenius type of argument. So suppose that the walker makes n steps in some time t. So here the time step t, and suppose that it moves n steps. So because it's a random walk, so the typical distance moved will be square root of n because it's a diffusion in steps basically. So k typical, the typical distance will be square root of n, but n itself, depends, number of steps depends on the history of the process, and how to estimate that. So you see again, I use this exactly same argument as used here. So 1 over pk or 1 over the transition probability, that's just the typical time to make one successful step. So if it makes n successful steps, then this is the total time basically. Okay, so this is the total time, and therefore the n, the number of steps moved, will scale like t times pk, but pk is 1 over mod k, so it's 1 over k typical. Okay. So now I substitute this guy here, and so you see that k typical goes like square root of t over k typical, and therefore just by simple scaling argument, you see that the k typical will go like t to the power 1/3. So it's a subdiffusive growth at late times, less subdiffusive in the sense is smaller than t to the power half, like normal diffusion. And we'll see that later, and we'll see that this is actually exact. I mean, you can actually prove this. Okay. But this already gives you a sort of interesting result that, this goes like t to the 1/3 scale, essentially. Okay. So first I'll focus on the position distribution. That's the first observable. So position distribution, again, you can write down the master equation. So it's very simple. So if the particle is at k at time t plus 1, it was at k minus 1 at time t, and then it make a jump from k minus 1 to k with this probability. And if it was at k plus 1, it makes this. It's just a simple Markov rule, and this is the staying probability at site k. Okay. So this, of course, you can solve for all t by generating function method, but I'll not, because it's a bit more complicated and long calculation. So what I'll do in this talk is just to show you that how to solve it in the continuum limit, because eventually what we want is the large time, large distance behavior position distribution, and for that it's simpler to again take the continuum limit. That means you assume that k is very large and t is large, and then you just make a Taylor expansion of this, and then you just get a Fokker-Planck equation. And the Fokker-Planck equation is very, very simple actually. So it's just del t pkt is a Laplacian, and inside there is a 1 over k pkt. Okay? So if you expand this Laplacian, you can actually write this as in this form, del k usual diffusive form. So this is like a space-dependent diffusion constant here, d of k, which goes like 1 over k. I'm looking at only positive side and symmetrically on the other side, but let's say k is positive, so I'm just looking on this side. So dk goes like 1 over k, and in addition, there is a drift or external potential, if you like, which also goes like 1 over k, and it's repulsive potential away from the origin. Okay? So this is the sort of continuum version of this model, that you have a both diffusion which is actually slowing down as it's going like 1 over k. The farther the particle goes, it moves much slower, and so that's why you call it a sluggish actually, because it becomes very difficult to move. And in addition, there is a repulsive potential, there is a repulsive force away from the origin, which is trying to push the particle, as 1 over k. The repulsive potential, that means the force is attractive actually towards the origin. And so this is the model, and we want to solve this model to find out what is P of kt. Okay? So, but this is the main point, that is, there is a diffusion constant which is space dependent, and also the drift or the external potential, which is also space dependent. Okay? So this is different from the Gillies model, because Gillies model, you remember, I discussed before, the Gillies model, dk was 1, the diffusion constant was 1, but the potential was 2 epsilon log k, and here it's actually 1 over k. So to solve this Fokker-Planck equation, so I mean, I already gave you a heuristic scaling argument that we expect that the k to scale like t to the 1/3. So then to solve this, you just assume that you just assume that for long time limit, scaling limit, it has a scaling form. This 1 over t to the power 1/3 is outside because it has to be normalized to 1. So integral of gz dz should be equal to 1 essentially. And so let's substitute this scaling form in this partial differential equation, and then that gives you see that indeed this is a right scaling form, because it gives a sort of closed second order differential equation for this g of z, and this is this differential equation. And remarkably, I mean, this equation doesn't look very easy to solve, but you find that it admits an exact solution. In fact, there are 2 linearly independent solutions, as it should. The first solution is just this. I'm looking at only the positive side, and similarly on this negative side, you have this symmetric form. So there's one solution which goes like z e to the power minus z cube over 3. So it's non-Gaussian, and plus it has a linear z. And the second solution is is just this guy here. Okay, you can check by substituting that this is indeed the exact solution, and then but the second solution, it turns out, is non-normalizable, which means that the square constant C2 must be equal to 0, and therefore we have the constant C1, which is fixed by the normalization condition, because if I look on the positive side, it's symmetric, so therefore this should be equal to half, and that gives us the exact scaling form, Gz. So now it's symmetric in Z, and it has a mod z e to the power minus mod z cube over 3 with a normalization constant, which is exactly this. Okay. So this is very nice, because this is sort of exact solution. And then we did a numerical simulation to check, and if you plot this function, what you see is it has a double peak structure with a hole at the center. And this hole is easy to understand because there is a repulsive potential away from the origin, which tries to push the particles, particle mass away from the origin. But then it gets sluggish as it goes farther and farther. So it never becomes stationary. It's still time dependent, because z is k over t to the power 1/3. But this center here, it moves as t to the power 1/3 essentially. And I mean, the scales like t to the power 1/3, the width here. And but it has this very nice non-Gaussian, and also it has a non-Gaussian tail as z cube, very faster, much faster than Gaussian. And in addition, there's this cusp here at the origin. And as I said, the cusp here, you can trace back to the fact that the drift term, the potential was 1 over k, therefore the force is minus derivative of the potential, which is 1 over k square. So it tries to drive the particle away from the origin, and that leads to the trough, the hole at the origin. Okay, so this is the first observable position distribution. And now I want to talk about the survival probability. So survival probability up to time t. So this means that imagine that the particle starts at the initial position k naught, and I define q k naught t, which is the survival probability, meaning that the probability that starting at k naught equal to k naught, which is bigger than equal to 1, the walker stays positive up to time t. Okay? So for this, it's actually easier to look at the backward master equation. So backward master equation, so you just ask what happens in the first time step. Okay, so you look at the trajectory up to time t plus 1, and you ask, okay, in the first time step, what happens, and then after that, t time steps. So in the first time step, if you know that k naught, so it can jump to the k naught minus 1 to the left with this probability, and once it jumps there, then it has to survive starting at k naught minus 1 up to time t. Similarly here, if it goes to the right, and this is the staying probability. Okay, so this is just the backward equation. It's easier to solve the backward equations. And the boundary condition is that if it starts exactly at k naught equal to 0, then of course it will be 0 because it won't survive. Okay, and if it starts very far away, then it should be equal to 1 because it definitely survives at up to any finite time t. So once again, again you can solve it by generating function method, but it's easier to look at the continuum limit, and in the continuum limit, this has this form here, and notice that in the forward Fokker-Planck equation, forward generator, this 1 over k was inside the Laplacian, but in backward generator, it's outside the Laplacian, and so it's actually much easier to solve and subject to these boundary conditions. Okay, you can solve it, and the solution again, you will guess that it should have a scaling form k naught over t to the power 133 is just for convenience. So if you substitute this into this, substitute the scaling form into this equation and use the boundary conditions, you get an ordinary differential equation which you can solve trivially, and this is the exact survival probability, but this is the incomplete gamma function. And so therefore, it behaves the scaling function here. It behaves for small z, it behaves linearly, and for large z, it approaches 1, but it approaches 1 as e to the power minus z cube over 3, much faster than Gaussian. And so this is the, and if you have to contrast with the normal random walk, the Brownian motion, for which again survival probability has this form, but now it's a square root of t, not t to the power 1/3. And this scaling function for Brownian motion is well known, and this is just the error function, 2 by root pi 0 to z to the power minus u square. So it decays, it approaches 1 as a Gaussian, but here it goes like z cube. And so for the sluggish walker, therefore, if I fix k naught and take the large time limit, so that means you have to look at this small argument behavior, and what you find is that survival probability decays like t to the power 1/3, and which means that the first passage probability, which is just minus del t of survival probability, decays like 1 over t to the power 4/3. For Brownian motion is t to the power 3 by 2, and here it's 4/3. Okay, so this is the survival probability. Now, you can also ask, what is the joint survival and position distribution? That means, what is the probability that starting at k naught, the walker stays positive up to time t and arrives at k exactly at time t? Okay? And so if we sum over the final position k, I get the survival probability, but you can actually calculate this PSKT, the joint distribution. So for fixed k naught of order 1, so again it has this scaling form, always this t to the power 1/3 scaling. And now this scaling function h of z, it has this again a double peak structure, but here now it's a quadratic and not cusp, not as in the position distribution. So the condition on the survival, it actually has a quadratic behavior at the center. Okay, so now I come to the final observable, which is the distribution of maximum till time t. So again, the same model, same hopping rules, and I look at a particular trajectory. I start at k naught, and I look at the maximal displacement m of t up to time t. This is time and this is space. So what is convenient is to actually look at the cumulative distribution of the maximum. So you ask, what is the probability that this maximum m of t of this trajectory is less than or equal to some number L? So this I called, this is like again like a solvable probability, but now the barrier is at L actually. So again, you can write down the backward equation for it and with the boundary condition, but now the boundary condition, that observing boundary is at k not equal to L. Earlier it was at origin, but now it's at k not equal to L. And for Brownian motion, it doesn't matter because it's a system is homogeneous. But here it's inhomogeneous, so the maximum displacement is not the same as the solvable probability. So you have to solve again this problem with L here explicitly. And okay, you can solve it. I'm not going into the details, but just to show you the result. So it turns out that the Laplace transform with respect to time of this cumulative distribution of the maximum for starting position at the origin is actually given by exactly by this function here, where bi is just this cousin of the area function that diverges as z goes to infinity. And you can analyze, so therefore this implies that at the long time limit it has a scaling form again, where the scaling function gz you can compute as the inverse Laplace transform of this bi function. But you can extract the asymptotics very easily, and so here is the sort of asymptotic behavior. So the scaling function of the distribution of the maximum. I remember for Brownian motion, this is just a half Gaussian, but here it's a much more complicated function, and it goes to a constant with this non-trivial constant as linearly, and for large z, large argument, it decays again as exponential minus z cube over 3. So this is a comparison to numerical simulation. All right, so I'm almost nearing my end of the talk. So you can generalize this model in many different ways. So for instance, I mean, I can just take this P of k as some constant b over mod k plus 2 to the power alpha. And where alpha equal to 1 is the previous case I discussed, and alpha equal to 0 would be just the Brownian motion. And so in this case, so this corresponds to having the trap lengths growing logarithmically, but with a prefactor, which now depends on this alpha here. And it turns out that changes because it's a marginal variable, so the coefficient matters, and it changes the behavior completely. You can again use the same scaling argument, heuristic scaling argument I had used before. Typical, k typical will go scale like square root of n, and again 1 over pk, which is the transition, the rate times n must be equal to t, and this gives you that n goes like t over k to the power alpha. You put it back there and you get k typical as t to the power 1 over alpha plus 2. So alpha equal to 0, ordinary Brownian motion, you get back the square root of t. For alpha equal to 1, the case I discussed, you get t to the power 1/3. In general, this is t to the power 1 over, and again, it's still subdiffusive. Okay. And so for this, again, I mean, if you look at the continuum limit of the Fokker-Planck equation, it now has the diffusion constant which goes like 1 over mod k to the power alpha, and the potential which goes like 1 over mod k to the power alpha also. And again, you can just try a scaling form solution of this, and it turns out that you can solve the scaling function exactly as before for general alpha, and it has this sort of non-trivial stretched exponential form. And similarly, the other observables like solvable probability and the maximum distribution can be also computed similarly. I won't go into the details. So now I'll talk about, very quickly, that there are many other observables that you can calculate for this general alpha model. And so, for example, one thing that we looked at recently is the occupation time, which is the time spent on the positive side. Okay, so you observe the process up to time t, and you ask out of this time t how much of time it's spent on the positive side. So this for Brownian motion, this is the famous arc-sine law, the distribution of this occupation time p of t given the window size t, and so for the generalized sluggish random walk model where you have this diffusion constant and drift like this, so you could actually compute this explicitly using a backward Feynman-Gauss approach, and what you can find is that this distribution of capital T, occupation time, is actually has this scaling form where this function f of alpha x is completely explicit, and it has this form like this. And in fact, for alpha equal to 0, you recover the famous Levy's arc-sine law, which is this guy. But for general alpha, this is the form. Okay, I mean, so this as a function of, if you plot it as a function of alpha, you see that the distribution actually has peaks at x equal to 1 and x equal to 0, that means the walk is very stiff. I mean, it has a much higher probability to be occupation time. The fraction is 1, that means it spends all the time on the positive side, and 0 means it spends all the time on the negative side. So that means these walks are very stiff. If it goes to one side, it tends to stick to that side. And this is the alpha dependence. And you can do a simulation, and it works extremely well. But actually, it turns out that this particular, the PDF is actually has appeared before in the probability literature, and it's called the Lamperti PDF. So Lamperti process is the following. So imagine that you have a renewal process. So you have an excursions. Okay, and this picture is not very representative. Excursions, you can have a positive excursions or negative excursions. They're not necessarily alternate as in this figure. It can be 2 successive positive returns, then negative returns, and so on. And imagine that there's an up-down symmetry, and these intervals between successive returns to the origin are statistically independent. So in that sense, it's a renewal process. And the return time distribution, okay, it has a power law tail as tau to the power minus 1 minus theta, where theta is between 0 and 1. So for this particular renewal process, Lamperti was able to compute the occupation time distribution. That means, again, what fraction of time it spends on the positive side. And he showed that the Lamperti PDF is given by this. And what you realize, parameterized by this theta, which is the return time distribution. What you realize in our problem, because the survival probability decays like 1 over t to the power 1 over alpha plus 2, which means that successive returns to the origin, again, is a renewal process, with theta is just 1 over alpha plus 2. And therefore, we recover essentially the Lamperti PDF. This is the alternative way of deriving this result. So let me just make a little connection with some other models that people have studied in the literature. So, I mean, sometimes, people write, the space-dependent diffusion, they write directly a Langevin equation. But of course, if you directly write a Langevin equation, you have to interpret in what sense, because it's space-dependent. So whether it's a Stratonovich prescription or whether it's Ito prescription. And so if it is Stratonovich prescription, then it turns out that the Fokker-Planck equation associated to this Langevin equation has this form. Okay? But on the other hand, and for the particular choice of x to the power minus alpha, people have studied the probability position distribution. Okay, so these are the recent papers. And on the other hand, if you make the thing that this is Ito prescription, then it turns out that the corresponding Fokker-Planck equation is exactly the same continuum form as our model. But it turned, but the point is that, in our model is a much more, microscopic lattice model, and you derive this directly by, taking the continuum limit, and you don't, by hand, you do not put in these diffusion constant. So in that sense, it's actually, you don't need to make any Ito or Stratonovich prescription. So let me now just conclude with a summary. So essentially, I discussed about the particle moving in a rugged landscape in an inhomogeneous environment. In particular, a particular sluggish random walk model, where with a particular choice of this hopping probability, which leads to an exact solution, and it corresponds in the continuum limit to a model where you have a diffusion constant, which decays as 1 over x to the power alpha for large x, and in the presence of a repulsive potential, which goes like 1 over mod x to the power alpha. And this leads to a subdiffusive growth at late times, and you can calculate all these different observables exactly for any alpha. And apart from these observables, I discussed the occupation time only, but we actually managed to calculate also the time of the maximum, the time at which the maximum occurs, or the last passage time till time t, the last time it crossed the origin before time t. So all these 3 observables for Brownian motion, they all have arc-sine laws. But here, it turns out that they all have very different distributions. They are not the same as arc-sine law, and neither of them are equal to each other. They are different laws, essentially. And you can calculate them explicitly, but I don't discuss here. And so it will be nice to, of course, generalize this model to higher dimensions. It should be straightforward, but that's an open problem, and it has not been calculated yet, as far as I know. So with that, I'll just end my talk, and just as a sort of very what should I say? So shameless advertisement. So this is a recent book that we wrote with my colleague Gregory Sher, and it just got published by Oxford University Press in last July. And this is about statistics of extremes and records in random sequences. And many of the techniques of the survival probability or the extreme value statistics that I discussed today, the basic techniques you can find in this book. So thank you very much for it.
So we have a few minutes for questions. Right.
I wanted to remark that there's yet another model that is related to the sluggish random walker. It was invented by Lamberto Rondoni, and he called it the slicer map. So this is a completely deterministic system. It's related to what's called an interval exchange transformation. Mm-hmm. And here's very simple. You take the unit interval, you fill it uniformly with points, you split it in the middle, you move from one part to the left, one to the right. And then you introduce a slicer, meaning this 1/2 interval you split at a certain point, which actually is very much related to the probability that you introduced, namely with the power law, 1 over k to the alpha. And then again you move particles to the left or back to the right. And this simple map on a variation of alpha gives you actually the full spectrum of anomalous diffusion, from subdiffusion, like your sluggish walker, even to superdiffusion, because you have a deterministic mechanism by which propagating fronts move in both directions. So I think this is quite
That's interesting. I didn't know about this model. Okay, so maybe I can
look at it. And one question is, so this model actually also produces non-trivial superdiffusion. Mm-hmm. As you're dealing with a trap model, I mean, you don't have it, but perhaps you could also revert it to
probably. So,
to generate superdiffusion.
Yeah, I mean here, as I said, I mean, our main motivation actually came from the biological system, microbial population growth of mutant population. So there it was quite natural that this is this law 1 over k to the power alpha, basically. So
we were actually wondering about the corresponding Fokker-Planck equations, but we didn't do it.
I see.
So that looks interesting, perhaps to your questions.
Oh, thank you. That's an interesting comment. Yes. Yeah.
I have a question about the potential repulsion from 0.
Yes.
Where does that come from? I understand that it spends less time because the traps are smaller.
Absolutely. Okay, so maybe I can discuss it here. So you see that, so from k to k plus 1, we have this, this hopping rate, which is, let's say, pk. Okay, but on the other hand, if you k plus 1 to k, the reverse rate is actually so it from side k to k plus 1, it goes with a certain rate, but from k plus 1 to k, it comes back with a higher probability, so lower probability. So this actually creates a sort of local drift to the right. So that's the sort of origin. So unlike in the Gillis model, here it's not put in by hand. It's just already inbuilt in this PK, basically transition probability.
I guess a very large K, right?
Sorry?
Only in the limit where K is large.
Yeah, sure. Yeah, definitely. Yeah.
Any other question?
Yes, please.
So just, I guess, phenomenologically speaking, comparing it to other models, so, where you have persistence, like in active matter, for instance, you tend to see super diffusion if you have, you don't have time reversal symmetry. So what's the key ingredient here that you have persistence, but you're very slow?
Yeah, I mean, essentially the diffusion constant itself, as the particle moves away from the origin, so there's a local drift, just pushing the particle away. But as it goes, it becomes more and more sluggish, right? So because the diffusion constant itself also goes down. So, it tries to move away from the origin, but it sort of becomes, very sluggish, so it doesn't move. And that's what leads to the slow dynamics, essentially. So.
Okay, since we are a bit off, so I think we continue the questions. We have a coffee break now, okay? Let's thank the speaker.